The universe is putting us in solitary confinement, and there's absolutely nothing we can do about it. Worse yet, most galaxies we can see are already unreachable. We're stuck in the Milky Way, and no matter how advanced our technology becomes, we might never escape. Today, we will explore why everything science fiction taught you about space exploration is wrong. And here is a question for you. If you could travel at 1 light year per second, where in the universe would you go first? Let me know in the comments. I will pin the most creative answer. Now let's begin. Right now, as you're watching this, something extraordinary is happening all around us. The universe is expanding, not like a balloon inflating into empty space, but space itself is stretching, growing, creating more distance between distant galaxies with every passing second. Scientists discovered this almost a century ago, back in 1929, when astronomer Edwin Hubble noticed something peculiar. Nearly every galaxy we could see was moving away from us. The farther away they were, the faster they seemed to be fleeing. But here's where things get interesting. While most of the universe is racing away from us at incredible speeds, our own galaxy, the Milky Way, sits nestled in what astronomers call the local group. Think of it as a cosmic neighborhood, a collection of more than 50 galaxies, all bound together by gravity. And at the heart of this neighborhood are two giants, our Milky Way and the Andromeda Galaxy, located roughly 2.5 million light-years away. Now you might be thinking, if the universe is expanding and pushing everything apart, why haven't these galaxies drifted away from each other? Why is Andromeda actually moving toward us at about 110 kilometers per second? Why, in fact, are we and Andromeda destined to collide in about 4 billion years? The answer reveals something profound about the forces at play in our cosmic backyard. You see, the expansion of the universe isn't strong enough everywhere. It's a subtle effect that only dominates over truly vast distances. On smaller scales, like within our local group, gravity reigns supreme. The combined mass of the Milky Way and Andromeda, along with all the dark matter surrounding them, creates a gravitational pull so powerful that it completely overwhelms the expansion of space itself. We're not just neighbors. We're gravitationally shackled together, locked in an eternal dance that will eventually merge our two galaxies into one enormous elliptical galaxy that astronomers have already nicknamed Milkomeda. But what about everything beyond our local group? What about those billions of other galaxies scattered across the cosmos? This is where our story takes a darker turn. Recent discoveries from cutting-edge observatories have revealed something that challenges everything we hoped about humanity's cosmic future. In late January of 2026, scientists from the University of Groningen published groundbreaking research in the journal Nature Astronomy. Using detailed computer simulations, they discovered that the Milky Way, Andromeda, and the entire local group sit trapped within an enormous sheet of dark matter, stretching approximately 32 million light-years across. Picture this. Our cosmic neighborhood isn't floating freely in the universe. Instead, we're embedded in a vast structure, sandwiched between two gigantic voids, regions of space that contain almost no matter at all. This dark matter sheet acts like cosmic glue, binding us together while the voids on either side push against us. The galaxies beyond our local group, those sitting outside this dark matter prison, are being carried away by the expansion of space, accelerating into the darkness, moving faster and faster with each passing moment. And here's the part that should make every space enthusiast pause: they're not coming back. Ever. The universe isn't just expanding, it's accelerating that expansion, driven by something we call dark energy, a mysterious force that makes up roughly 68% of all energy in the cosmos. Dark energy is pushing space to stretch faster and faster, and any galaxy that isn't already bound to us by gravity is being swept away beyond our reach. Let me paint you a picture of what this means. Imagine standing on a beach, watching ships sail toward the horizon. Now imagine that horizon isn't fixed, but racing away from you, getting farther with every heartbeat. The The ships aren't just sailing away, the ocean itself is stretching, carrying them faster than any engine could propel them. That's what's happening to distant galaxies right now. They're not just moving through space. Space itself is carrying them away from us at speeds that will eventually exceed the speed of light. Wait, you might say, doesn't Einstein's theory tell us nothing can move faster than light? You're absolutely right, nothing can move through space faster than light. But space itself isn't bound by that rule. Space can stretch at any speed it wants. And when it stretches fast enough, even light from distant galaxies can't fight against the current. Those galaxies cross what we call the cosmic event horizon, a boundary beyond which light emitted today will never, ever reach us, no matter how long we wait. Now here's something that might surprise you. We don't have to wait billions of years for this to happen. It's already happening right now. Every single day, galaxies are crossing our cosmic event horizon, disappearing from what will ever be reachable to us. Even if we could build a spaceship that travels at the speed of light, even if we left today, we could never catch up to these galaxies because the space between us and them is expanding faster than we could ever travel through it. Make sure you hit that subscribe button and give this video a thumbs up, because what I'm about to share next will completely change how you think about our place in the universe. Trust me, you don't want to miss this. The numbers are staggering. Right now, we can observe galaxies up to approximately 46.5 billion light-years away. That's the radius of our observable universe. But here's the twist. We can see those galaxies because their light was emitted billions of years ago when they were much closer to us and the universe was expanding more slowly. The light has been traveling toward us all that time, fighting against the expansion, but steadily making progress. However, if we tried to send a signal to those same galaxies today, our message would never arrive. They've already crossed our event horizon. Calculations suggest that only about 3% of the galaxies we can currently see in our telescopes remain within our reachable universe, what scientists call our future light cone. 97% of the galaxies visible in our night sky are already forever beyond our grasp. We can see them, we can study their light, we can learn their secrets from the past, but we can never go there. We can never send probes there. We can never communicate with any civilizations that might exist there. They exist in a realm that, for all practical purposes, has already separated from ours. Think about what this means for any potential alien civilizations watching us right now from distant galaxies. From their perspective, we're the ones slipping away, crossing their event horizon, vanishing into a part of the universe they'll never be able to explore. It's like we're all on different lifeboats drifting apart in an infinite ocean, able to see each other's lights growing dimmer and dimmer, but unable to ever reach each other again. And it gets even more profound. As time marches forward, our observable universe will actually shrink. Galaxies that we can see today will, one by one, cross the cosmic event horizon. Their light will become increasingly redshifted, stretched by the expanding space until it fades to darkness. In about 150 billion years, every galaxy beyond our local group will have disappeared from view. Any astronomers living then, perhaps on a planet orbiting a star born from the merger of the Milky Way and Andromeda, will look out into the night sky and see nothing but darkness beyond their own galaxy. They'll have no way of knowing that billions of other galaxies once existed, no evidence of the Big Bang, no ability to discover that the universe is even expanding. So let's talk about why this cosmic prison exists in the first place. What forces conspired to trap us here, and is there any possible way out? To understand this, we need to dive into one of the most mysterious substances in the universe, dark energy. Back in 1998, two independent teams of astronomers made a discovery that shocked the scientific world. They were studying distant supernovae, stellar explosions so bright they can outshine entire galaxies for weeks. These supernovae serve as cosmic measuring sticks because we understand exactly how bright they should be. By comparing their actual brightness to their expected brightness, we can calculate how far away they are with remarkable precision. What these astronomers found defied all expectations. The distant supernovae were dimmer than they should be, which meant they were farther away than predicted. But here's the kicker. These supernovae weren't just far away, they were farther than they should be if the universe had been expanding at a constant rate. The only explanation that made sense was that the expansion of the universe hadn't been constant at all. It had been accelerating. Imagine throwing a ball straight up into the air. You expect gravity to slow it down, right? But instead, the ball starts speeding up, flying faster and faster away from you. That's essentially what these astronomers discovered happening to the entire universe. Something was pushing against gravity, causing the expansion to accelerate rather than slow down. They called this mysterious force dark energy, and the discovery earned them the Nobel Prize in Physics in 2011. Now here's where things get really wild. Dark energy doesn't just exist in small amounts scattered here and there throughout the cosmos. It dominates everything. When scientists add up all the mass and energy in the entire universe, they find that roughly 68% of it is dark energy. Another 27% is dark matter, the invisible substance that holds galaxies together through its gravitational pull. And regular matter, the stuff that makes up stars, planets, you, me, everything we've ever seen or touched, makes up less than 5% of the universe. We're basically living in a cosmos made almost entirely of things we can't see, don't fully understand, and can barely detect. Dark energy behaves unlike anything else we know. While matter, and even dark matter, clump together due to gravity, dark energy remains perfectly smooth, spread evenly throughout space. It doesn't dilute as the universe expands. In fact, as space stretches and creates more volume, dark energy fills that new space with the same density it had before. This means that while the gravitational pull of matter gets weaker as the universe grows larger and more spread out, dark energy maintains its strength, pushing space apart with relentless consistency. Think of it like this. Imagine a tug-of-war between gravity trying to pull everything together and dark energy trying to push everything apart. In the early universe, matter was packed tightly together and gravity dominated completely. But as the universe expanded and matter spread out, gravity's grip weakened. Meanwhile, dark energy stayed just as strong as ever. About 6 billion years ago, somewhere around the time complex life was emerging on Earth, dark energy finally won the cosmic tug-of-war. From that point forward, the expansion of the universe has been accelerating. But here's something absolutely crucial to understand. Dark energy only dominates over large distances. Within our local group, the gravitational attraction between galaxies is still far stronger than the repulsive effect of dark energy. That's why Andromeda is moving toward us rather than away. That's why our local group remains bound together. Gravity hasn't lost everywhere, only across the vast gulfs between galaxy clusters. Recent research published in February 2026 suggests something even more dramatic. A physicist from Cornell University named Henry Tai analyzed the latest data from dark energy observatories and calculated that dark energy might not remain constant forever. Instead, it could be changing in ways that will fundamentally alter the fate of the universe. His calculations suggest that in approximately 11 billion years, the universe will reach its maximum size. After that, dark energy might flip from pushing space apart to pulling it back together. If he's right, and I want to stress this is still a hypothesis being debated by scientists, the universe won't expand forever into cold darkness. Instead, it will reverse course. Galaxies that have been racing apart will begin falling back toward each other. The expansion will become a contraction. And in roughly 20 billion years from now, everything, every galaxy, every star, every atom could collapse back into a single point in what scientists call the Big Crunch, a mirror image of the Big Bang that started everything. Now, before we get too caught up in cosmic doomsday scenarios, let me remind you that we're talking about timescales so vast they're almost incomprehensible. 20 billion years is more than the current age of the entire universe. Our sun will have exhausted its fuel and died billions of years before any of this happens. But the point is this: the nature of dark energy determines not just whether we can escape our cosmic prison, but the ultimate fate of everything that exists. Speaking of escape, let's explore what it would actually take to leave our local group and visit another galaxy cluster. If you haven't already, I highly recommend checking out my video called The Absolute Limit of Human Travel Through Space, where I dive deep into the physics of interstellar journeys. But here's the short version. Even reaching the nearest stars in our own galaxy requires technology far beyond anything we currently possess. Traveling to another galaxy cluster? That's on a completely different level of impossible. The link of the video is in the description and on the card above. The Virgo cluster, one of the nearest major galaxy clusters to us, sits approximately 55 million light-years away. To give you perspective, traveling at 300,000 kilometers per second takes 55 million years to cross that distance. Even if we could build a spaceship that travels at 99% the speed of light, a journey to Virgo would take tens of millions of years, and that's not accounting for the fact that space is expanding. By the time we arrived, Virgo would have moved even farther away than when we started. But let's say, just for fun, that we develop some revolutionary technology. Maybe we figure out how to create wormholes, shortcuts through space-time, that could theoretically let us jump from one location to another without crossing the space in between. Or maybe we discover some way to manipulate space itself, creating a warp drive that contracts space in front of our ship and expands it behind us, letting us surf on a wave of space-time. These ideas don't violate the known laws of physics, but they require forms of matter and energy that we've never observed and don't know how to create. Even if we solved all these technical challenges, we'd still run into the cosmic event horizon problem. Remember those galaxies receding faster than light? No technology, not wormholes, not warp drives, not anything we can imagine, can overcome the fundamental expansion of space itself. Once a galaxy crosses our event horizon, it's gone from our reachable universe forever, no matter what we invent. Here's another sobering thought: time dilation. According to Einstein's theory of relativity, as you approach the speed of light, time slows down for you relative to the rest of the universe. If you traveled to a distant galaxy at near light speed, you might experience the journey as taking only a few years or decades. But back on Earth, millions or billions of years would pass. You could return home to find that not only has everyone you knew died long ago, but Earth itself might be a barren rock orbiting a dying sun. Civilization as you knew it would have risen and fallen countless times. You'd be a time traveler, stranded in an unrecognizable future. Now let's talk about something that might give you chills: the lonely future waiting for any civilization that survives long enough to witness it. We've established that we're trapped in the Milky Way and our local group, but what does this actually mean for the distant future of intelligence in the universe? Imagine you're an astronomer living 100 billion years from now. The Milky Way and Andromeda have long since merged into Milkomeda, a giant elliptical galaxy filled with older, redder stars. Many of the brightest, most massive stars from our era have already exploded as supernovae or collapsed into black holes. New star formation has slowed dramatically because galaxies have used up most of their gas and dust. The universe is entering what scientists call its middle age. You point your telescope outward, searching for other galaxies, other islands of stars in the cosmic ocean, but you find nothing. The sky beyond your galaxy is completely black. Not a single external galaxy remains visible. They've all crossed the cosmic event horizon, carried away by the relentless expansion of space. Their light, stretched by billions of years of expansion, has redshifted beyond detection, fading into the cosmic microwave background radiation until it's indistinguishable from the leftover glow of the Big Bang itself. Here's what makes this scenario truly profound. If you were a scientist in that distant era, you'd have no way of knowing that other galaxies ever existed. You couldn't discover that the universe is expanding because you'd have nothing external to measure that expansion against. You couldn't detect the cosmic microwave background radiation because it would have cooled and redshifted to the point of being essentially undetectable with any reasonable technology. You couldn't prove the Big Bang happened because all the evidence would have literally disappeared beyond your cosmic horizon. Your entire observable universe would consist of a single galaxy floating in eternal darkness. You might theorize about other galaxies existing somewhere beyond what you can see, but you'd have no evidence, no way to test your theories, no means of knowing whether you're right. In essence, the universe would have erased its own history, locked away its secrets beyond an impenetrable barrier of expanding space. This raises an unsettling question. Could we be in a similar situation right now? Could there be aspects of the universe, entire regions or phenomena that existed in the deep past but have already crossed beyond our cosmic horizon? Evidence that we'll never see because it's been carried away by expansion? Scientists think the answer is probably yes. In fact, our observable universe, as vast as it is, likely represents only a tiny fraction of the total universe that exists beyond what we can ever see. The cosmic microwave background, that faint afterglow of the Big Bang that fills all of space, represents the oldest light we can detect. It was emitted about 380,000 years after the Big Bang, at the moment when the universe cooled enough for atoms to form and light to travel freely through space. But what about everything that happened before that moment? What about the first 380,000 years of cosmic history? That information is hidden behind an impenetrable curtain. Light from that era scattered off free electrons so many times that it never traveled far before being absorbed or redirected. We can't see through that fog, no matter how powerful our telescopes become. And if theories about cosmic inflation are correct, if the universe underwent a brief period of exponentially rapid expansion in the first fraction of a second after the Big Bang, then the vast majority of the universe, perhaps even an infinite portion of it, has always been beyond our cosmic horizon. We're not just trapped in our local group of galaxies, we're trapped in a bubble of space-time, surrounded by unreachable realms that might contain wonders and mysteries we can't even imagine. Let's bring this back to something more immediate. What about exploring our own galaxy? Surely we're not trapped on Earth forever, right? Well, here's where things get complicated. The Milky Way is enormous, containing somewhere between 100 billion and 400 billion stars spread across a disk roughly 100,000 light-years in diameter. Our Sun sits about 26,000 light-years from the galactic center, roughly halfway out in one of the spiral arms. The nearest star to us, Proxima Centauri, is approximately 4.2 light-years away. That might not sound too bad until you realize that with our current fastest spacecraft, New Horizons, which is speeding away from the solar system at about 58,000 kilometers per hour, it would take over 73,000 years to reach Proxima Centauri. That's longer than all of recorded human history, and Proxima Centauri is our closest neighbor. Most stars in the galaxy are thousands or tens of thousands of light-years away. Even if we develop propulsion systems that can reach a significant fraction of light speed, say 10%, traveling across the galaxy would still take 1,000,000 years. And remember, the galaxy isn't static. Stars orbit the galactic center at different speeds depending on their distance from the center. Our Sun completes one orbit approximately every 230 million years, a period astronomers call a cosmic year. By the time a spacecraft launched from Earth today crossed the galaxy, the entire stellar landscape would have shifted. Stars we aimed for would have moved. New stars would have formed. Old stars would have died. But here's something even more challenging: radiation. Space isn't empty. It's filled with high-energy particles, cosmic rays, that stream through the galaxy at nearly the speed of light. Earth's magnetic field and atmosphere protect us from most of this radiation, but a spacecraft traveling through interstellar space, especially at high speeds, would be bombarded by these particles constantly. At near-light speeds, even tiny dust grains become catastrophic threats. Hitting a grain of sand while traveling at 90% light speed would release energy equivalent to a large bomb. Traveling fast through space isn't just difficult, it's incredibly dangerous. Then there's the energy problem. Accelerating even a small spacecraft to a significant fraction of light speed requires absolutely staggering amounts of energy. To accelerate a 1-ton spacecraft to half the speed of light would require approximately 6.7 times 10 to the power of 17 joules of energy. That's more energy than the entire human civilization currently produces in a year. And that's just to accelerate. You'd need nearly the same amount of energy again to slow down when you reach your destination, unless you're okay with flying past at half-light speed, which wouldn't give you much time to take photos. Various theoretical propulsion systems have been proposed to solve this problem. Nuclear fusion rockets could potentially achieve a few % of light speed. Antimatter engines, if we could produce and contain antimatter safely and efficiently, might reach 10 or 20%. Laser sail technology, where Earth-based lasers push against enormous reflective sails, could theoretically accelerate small probes to relativistic speeds. But all of these technologies face enormous practical challenges, and none of them get us anywhere close to escaping our cosmic prison. There's also the problem of navigation. Space is vast and mostly empty, but that emptiness isn't perfect. Interstellar space contains about 1 atom per cubic centimeter on average, mostly hydrogen. That doesn't sound like much, but when you're traveling at relativistic speeds through light years of space, those atoms add up. They create drag, they cause erosion, they generate heat. Long-distance space travel at high speeds isn't like sailing smoothly through an ocean. It's more like sandblasting your spacecraft continuously for decades, centuries, or millennia. And let's not forget about the human element. Even if we solve all the technical challenges, could humans actually survive journeys lasting thousands or millions of years? Generation ships, vessels that would house multiple generations of people born, living, and dying en route to distant stars, face enormous biological and social challenges. How do you maintain genetic diversity in a small population? How do you preserve knowledge and purpose across hundreds of generations? How do you prevent social collapse, conflict, or loss of mission focus during a voyage that outlasts entire civilizations? Some scientists propose sending frozen embryos and having artificial intelligence raise the first generation upon arrival. Others suggest uploading human consciousness into computers, letting digital minds explore the galaxy while our biological bodies stay behind. These ideas edge closer to science fiction than engineering, but they represent serious attempts to grapple with the fact that biological humans, as we currently exist, are fundamentally unsuited for interstellar travel. Let's explore something that might sound like science fiction, but is actually grounded in serious physics. Could we ever manipulate space-time itself to escape our cosmic prison? After all, if the expansion of space can carry galaxies away faster than light, maybe we could harness similar phenomena to travel in ways that bypass the normal limits of speed. The most famous idea along these lines is the Alcubierre drive, named after Mexican physicist Miguel Alcubierre, who proposed it in 1994. The concept is elegant. Instead of moving through space, you move space itself. The drive would contract space-time in front of your ship while expanding it behind you, creating a wave of curved space-time that carries your vessel along with it. From your perspective inside the ship, you'd never actually accelerate. You'd just surf along on this bubble of warped space, potentially crossing vast distances in relatively short periods. Here's the beautiful part. This concept doesn't violate Einstein's cosmic speed limit. Light speed is still the maximum velocity for anything moving through space, but the Alcubierre's drive wouldn't be moving through space in the traditional sense. Space itself would be doing the moving. It's the same principle that allows distant galaxies to recede from us faster than light due to cosmic expansion. Einstein's equations don't forbid space itself from expanding or contracting at any speed. Sounds perfect, right? Not so fast. The Alcubierre drive faces problems so severe that most physicists consider it practically impossible, at least with any technology we can envision. First, it requires something called negative energy, or exotic matter, a form of matter with negative mass that would push space-time outward instead of pulling it inward like normal matter does. We've never observed negative mass in nature. Some quantum effects produce tiny amounts of negative energy under specific conditions, but scaling this up to warp space-time around a spacecraft would require amounts of negative energy that might exceed the total mass energy of observable galaxies. Second, even if you could create an Alcubierre bubble, you couldn't control it from inside. The front of the bubble, where space is contracting, would be causally disconnected from the interior. You couldn't send signals to it or manipulate it in any way. It's like trying to steer a boat by standing at the back and pushing the front, except the front is beyond your reach, beyond your ability to even see or communicate with. You'd need some external mechanism to create, direct, and collapse the warp bubble, which kind of defeats the purpose of having a warp drive in the first place. Third, recent calculations suggest that particles and radiation would accumulate at the front of the warp bubble during travel. When you finally stopped and the bubble collapsed, all that accumulated energy would be released in a catastrophic blast that could destroy anything in front of your ship, including your destination. Imagine traveling to a distant star system only to sterilize it with a burst of deadly radiation the moment you arrive. Not exactly the friendly first contact we'd hope for, but let's say, hypothetically, we solve all these problems. We figure out how to produce exotic matter, control the bubble, and prevent the deadly radiation buildup. Would an Alcubierre drive let us escape to other galaxy clusters before they cross our cosmic event horizon? Probably not. Here's why. The space between galaxy clusters isn't static. It's actively expanding, stretching at rates that increase with distance. The Alcubierre drive would let you move quickly through space as it exists at any given moment, but it wouldn't stop space from continuing to expand while you're traveling. Think of it like running on a treadmill that keeps speeding up. Even if you can run very fast, if the treadmill accelerates faster than you can increase your speed, you'll still fall behind. The expansion of space between us and distant galaxy clusters is accelerating due to dark energy. Eventually, that expansion rate exceeds what even a hypothetical warp drive could overcome. The galaxies aren't just far away, they're receding at an accelerating rate that makes them fundamentally unreachable. What about wormholes? These theoretical tunnels through space-time could potentially connect two distant points in the universe, allowing instantaneous travel between them without crossing the space in between. Einstein's equations actually permit wormhole solutions. They're mathematically consistent with general relativity. But once again, we run into the exotic matter problem. To keep a wormhole open and stable enough for something to pass through, you'd need enormous amounts of negative energy to counteract the intense gravitational forces trying to collapse it. Even more problematic, you can't just create a wormhole between Earth and a distant galaxy. You'd need to physically travel to that galaxy first, using conventional means to place the other end of the wormhole there. It's like trying to build a tunnel through a mountain. You need access to both ends to dig from both directions. If you could already reach that distant galaxy, you wouldn't need the wormhole in the first place. Wormholes might be useful for repeated travel between two locations, but they don't solve the problem of reaching somewhere for the first time. There's also the causality problem. Some wormhole configurations could theoretically allow travel backward in time, creating paradoxes that might be physically impossible. If you could travel through a wormhole to a distant galaxy and then return through another wormhole, the time dilation effects might let you arrive back home before you left. This creates the famous grandfather paradox, where you could theoretically prevent your own existence. Most physicists believe the universe has some mechanism, possibly at the quantum level, that prevents such paradoxes from occurring, which might mean stable traversable wormholes are simply impossible. Let's talk about black holes for a moment because they're relevant to this discussion in a surprising way. Black holes are regions of space-time where gravity is so intense that nothing, not even light, can escape once it crosses the event horizon. In some ways, our cosmic predicament mirrors what happens near a black hole. Just as anything crossing a black hole's event horizon is trapped forever by gravity, galaxies crossing our cosmic event horizon are trapped forever beyond our reach by expansion. But here's an interesting twist. The mathematics describing black hole event horizons and cosmic event horizons are eerily similar. Both involve limits on what can be observed or reached. Both create boundaries that divide space-time into regions that can and cannot communicate with each other. Some physicists speculate that this similarity might not be coincidental, that it might point to some deeper truth about the nature of space-time itself. Recent theoretical work has explored the idea of using the extreme gravity near black holes as a form of natural time dilation. If you could orbit very close to a black hole's event horizon without falling in, time would slow down dramatically for you relative to the rest of the universe. You could wait there for millions or billions of years of external time while experiencing only months or years personally. In principle, you could use this to wait out the journey to a distant location, letting the universe age around you while you remain effectively frozen in time. But this strategy doesn't help with galaxies receding due to cosmic expansion. Time dilation lets you skip forward through time, but it doesn't change the fact that those galaxies are moving away faster than light. Whether you experience the journey as taking 1 year or 1 billion years, the destination is still receding beyond your reach. It's like watching a ship sail over the horizon. Closing your eyes doesn't bring the ship back. What about using the energy of black holes themselves? Roger Penrose proposed a mechanism back in 1969 showing that you could theoretically extract energy from a rotating black hole by dropping matter into it in specific ways. More recently, scientists have suggested that advanced civilizations might surround black holes with structures to capture the intense radiation emitted by infalling matter, creating power sources far more efficient than stars. If we could harness such enormous energies, could we power propulsion systems capable of reaching distant galaxies? The answer is still no, for the same fundamental reason. You can't outrun the expansion of space itself, no matter how much energy you have. Energy lets you accelerate to higher speeds, but Einstein's equations still cap your maximum velocity at the speed of light relative to local space-time. And once a galaxy is receding faster than light due to expansion, no amount of energy can catch it, because you're not just fighting its motion through space, you're fighting the creation of new space between you and it. Here's something that might surprise you. Even if we could somehow travel infinitely fast, we still couldn't reach galaxies beyond our cosmic event horizon. Infinite speed through space would mean you could go from here to anywhere else in 0 time, right? But when space itself is expanding, adding new distance faster than you can cross it, even infinite speed isn't enough. It's like trying to run from the back of an infinitely long train to the front, while someone keeps adding more cars to the train faster than you can run past the existing ones. You'll never reach the front, no matter how fast you run. This isn't just a technological limitation, it's a fundamental feature of the universe we inhabit. The laws of physics themselves, as we currently understand them, create an absolute boundary around what we can ever reach. No amount of technological advancement, no matter how clever or powerful, can overcome this limitation unless the laws of physics themselves are different than we think. So if we're trapped in the Milky Way and our local group, what does this mean for one of humanity's biggest questions? Are we alone in the universe? The search for extraterrestrial intelligence, or SETI, has been scanning the skies for radio signals from alien civilizations for over 60 years. We've pointed our telescopes at thousands of star systems, listening for any hint of artificial signals, any whisper of intelligence reaching across the cosmic void. So far, we've heard only silence. But maybe we've been thinking about this problem all wrong. Consider this. If an advanced civilization exists in a galaxy beyond our local group, and they're facing the same cosmic expansion we are, then they're trapped just like us. They can see our galaxy in their telescopes just as we can see theirs, but the space between us is stretching faster than light can cross it. Even if they developed perfect communication technology and sent us a message today, that message would never arrive. It would be like shouting across an ocean that keeps growing wider, your voice fading into the distance, never reaching the other shore. Now here's the truly sobering part. Most galaxies we can see in the night sky are already beyond our cosmic event horizon. The Virgo cluster, containing about 1,500 galaxies, sits 55 million light-years away. The Coma cluster, with over 1,000 galaxies, is roughly 320 million light-years distant. The Hercules cluster, Hydra cluster, Perseus cluster, each containing hundreds or thousands of galaxies, all spread across hundreds of millions of light-years. If intelligent civilizations exist in those galaxies, and statistically, some almost certainly do, given the billions of stars each galaxy contains, we can see their past but never interact with their present or future. Think about what this means. There could be civilizations out there right now at this very moment, facing the same existential questions we are, looking up at their night sky and wondering if anyone else is out there. They might have developed radio, television, spaceflight. They might be broadcasting signals announcing their presence to the cosmos, but we'll never hear those signals because the space between us is expanding too fast for light to bridge the gap. We're like prisoners in adjacent cells, able to see each other but unable to speak, unable to touch, separated by an impenetrable barrier that grows thicker with every passing moment. But let's focus on what we can potentially reach, our local group. Remember, this is the collection of more than 50 galaxies gravitationally bound together, including the Milky Way, Andromeda, and the Triangulum galaxy, along with dozens of smaller dwarf galaxies. The entire local group spans about 10 million light-years across. Within this cosmic neighborhood, gravity overpowers the expansion of space. These galaxies aren't receding from us. They're our permanent companions through cosmic time. So the real question becomes, could there be intelligent life elsewhere in our local group? The Andromeda galaxy is similar to the Milky Way, containing roughly 1 trillion stars. That's about twice as many as our galaxy. The Triangulum galaxy, the third largest member of our local group, holds perhaps 40 billion stars. Even the dwarf galaxies, tiny by comparison, contain millions to billions of stars each. Add it all up, and our local group contains somewhere around 2 to 3 trillion stars total. Now, we don't know how common life is in the universe. We don't know how often life, once it emerges, develops intelligence. We don't know how long technological civilizations typically survive before destroying themselves or going extinct. These are the famous variables in the Drake equation, a mathematical formula designed to estimate the number of detectable civilizations in a given volume of space. But even with conservative estimates, 2 to 3 trillion stars represent an enormous number of potential homes for life. Here's what makes this especially interesting. We could theoretically communicate with civilizations anywhere in our local group, at least in principle. A radio signal sent from Earth would take about 2.5 million years to reach Andromeda, and another 2.5 million years for their reply to reach us. That's not a conversation in any normal sense. It's more like leaving a message for a civilization that might not even exist yet, and hoping their distant descendants find it and respond. But it's possible. The laws of physics don't forbid it. Contrast this with galaxies beyond our local group. The Virgo cluster, for example, is already receding from us at about 1,200 kilometers per second. That's roughly 0.4% of light speed. While this isn't fast enough yet to prevent light from eventually reaching Virgo, the acceleration means that signals we send today would take progressively longer to arrive as space continues expanding during their journey. More distant clusters are receding even faster. The Coma cluster is moving away at about 7,000 kilometers per second, over 2% of light speed, and the farther you look, the faster the recession speed becomes. There's a distance, calculated to be roughly 15 billion light-years in the current epoch, beyond which galaxies are receding faster than light. We can still see these galaxies because the light now reaching us was emitted billions of years ago when they were closer and receding slower. But if we sent a signal toward them today, that signal would never arrive. The expansion of space would stretch the distance faster than the signal could cross it. Those galaxies exist in a realm we can observe but never contact, a cosmic display case of worlds forever beyond our reach. Let's talk about the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" The paradox points out an apparent contradiction. The universe is vast and ancient, containing billions of galaxies with trillions of stars, many of them billions of years older than our Sun. If intelligent life is even moderately common, the galaxy should be teeming with civilizations, some of them far more advanced than us. So why haven't we detected any signs of them? Why haven't they visited Earth? Why does the universe seem so empty? Many solutions to the Fermi paradox have been proposed. Maybe intelligent life is incredibly rare. Maybe civilizations tend to destroy themselves shortly after developing advanced technology. Maybe they're deliberately hiding from us. Maybe they exist in forms so different from us that we can't recognize their signals or artifacts. But here's another possibility that cosmic expansion adds to the mix. Maybe advanced civilizations do exist. Maybe they're even common, but they're scattered across different galaxy clusters that can never communicate with each other due to cosmic expansion. Picture the universe as a vast archipelago of island groups, each containing dozens or hundreds of galaxies bound together by gravity. Within each island group, civilizations could potentially communicate, travel between worlds, build an interconnected society spanning multiple galaxies. But between the island groups, the ocean of expanding space grows wider every moment, making contact between groups progressively more difficult and eventually impossible. Each island group develops in isolation, never knowing about the others, each cluster of galaxies becoming its own separate cosmic civilization. If this is correct, then the answer to Fermi's question might be, everybody is out there, just not in places we can ever reach or hear from. The universe could be filled with intelligence, but that intelligence is fragmented into isolated pockets, cosmic communities that can never meet. We're not alone in the universe as a whole, but we might be forever alone in our particular corner of it. This has profound implications for how we think about our cosmic future. Instead of imagining humanity one day joining a galactic community of thousands of species or spreading across the entire universe to encounter countless alien worlds, we need to think smaller and more locally. Our ultimate cosmic neighborhood isn't the universe, it isn't even the observable universe, it's just our local group. These 50-plus galaxies containing 2 to 3 trillion stars represent the total scope of what humanity or any civilization in our local group could ever potentially explore or colonize. 2 to 3 trillion stars still sounds like a lot, and it is. That's an almost incomprehensibly vast frontier. If humanity somehow survives long enough to become a spacefaring civilization capable of settling other star systems, we'd have enough worlds to explore for billions of years. The Milky Way alone would take millions of years to fully explore, even with very fast spacecraft. Adding Andromeda, Triangulum, and the dwarf galaxies gives us enough real estate to keep us busy essentially forever from any practical perspective. But there's something psychologically different about knowing you're in a limited cosmic bubble versus imagining yourself part of an infinite universe full of possibilities. It's the difference between living on a large but finite island versus living on a continent that stretches endlessly in all directions. The island might be big enough for all practical purposes, but knowing its boundaries exist changes how you think about your place in the world. Let's talk about the most dramatic event in our cosmic neighborhood's future, the collision between the Milky Way and Andromeda. This isn't some distant theoretical possibility. It's an inevitable cosmic smash-up that's already in progress. Right now, at this very moment, Andromeda is hurtling toward us at roughly 110 kilometers per second. That's about 246,000 miles per hour, and there's nothing that can stop it. Now, before you panic, let me clarify what we mean by collision. When galaxies collide, it's not like two cars crashing into each other. Galaxies are mostly empty space. The distances between stars are so vast that even when two galaxies merge, the individual stars almost never actually hit each other. If you were standing on a planet in a solar system during a galaxy collision, you probably wouldn't notice anything dramatic happening in the short term. The stars in the other galaxy would gradually become mixed with your own. The night sky would slowly change over millions of years, but your own star and planet would likely pass through the entire event unscathed. However, that doesn't mean galaxy collisions are gentle affairs. The gravitational interactions between billions of stars create chaos on a grand scale. Stars get flung out of their normal orbits. Some get ejected from the galaxies entirely, becoming intergalactic wanderers drifting through the void. Gas clouds that were peacefully orbiting within each galaxy slam into each other, compressing and heating up, triggering massive bursts of new star formation. The night sky would light up with brilliant young stars and spectacular supernova explosions as massive stars burn through their fuel and die. Computer simulations show us exactly what will happen when the Milky Way and Andromeda meet. In about 4 billion years, roughly around the time our Sun will be nearing the end of its stable life, Andromeda will loom enormous in Earth's night sky, no longer a faint smudge, but a brilliant spiral stretching across the heavens. The two galaxies will pass through each other in their first encounter, their mutual gravity stretching them into distorted shapes, pulling out long streamers of stars. But they won't escape each other's gravitational embrace. Like two dancers locked in a cosmic waltz, they'll swing back around for a second pass. This time, the collision will be even more violent, as the galaxies have less angular momentum to keep them apart. The spiral structures will be largely destroyed, stars scattered into more chaotic orbits. Gas and dust lanes will collide, producing spectacular fireworks of star formation across the merged system. After several passes over the course of about 2 billion years, the two galaxies will finally settle into a single structure. The elegant spiral arms will be gone, replaced by a more spherical shape characteristic of elliptical galaxies. Astronomers have already nicknamed this merged galaxy Milkomeda, a combination of Milky Way and Andromeda. Milkomeda will be a giant elliptical galaxy containing perhaps 2 trillion stars, making it one of the largest galaxies in our cosmic neighborhood. But here's something most people don't realize. Earth and our solar system will probably survive this cosmic catastrophe just fine. The chance of our Sun actually colliding with another star during the merger is incredibly tiny, less than 1 in several billion. Stars are simply too small and too far apart for direct collisions to be likely. However, our Sun's orbit within the galaxy will almost certainly change. We might end up much closer to or farther from the galactic center. We might even be one of the unlucky stars ejected entirely from the merged galaxy, spending the rest of eternity drifting through intergalactic space. If Earth does get flung into intergalactic space, the view would be spectacular and terrifying. Instead of seeing the Milky Way as a band across the sky, you'd see the entire galaxy, now merged with Andromeda, as a brilliant elliptical blob hanging in the darkness. There would be no other galaxies visible nearby, just Milkomeda and the much smaller dwarf galaxies of our local group, separated by millions of light-years of empty space. The night sky would be darker than anything we experience today, with far fewer stars visible. But honestly, by the time this merger happens, Earth as we know it will likely already be uninhabitable for other reasons. Our Sun is gradually getting hotter as it ages. In about 1 billion years, maybe sooner, Earth's oceans will boil away. The runaway greenhouse effect will turn our planet into something resembling Venus, a scorched hellscape with surface temperatures hot enough to melt lead. Any life that survives will need to migrate to the outer solar system, to moons like Europa or Titan that will become more hospitable as the sun heats up. And in about 5 billion years, the sun will exhaust the hydrogen fuel in its core and begin its transformation into a red giant. It will swell dramatically, its outer layers expanding to perhaps engulf the orbits of Mercury and Venus. Earth might survive, pushed into a more distant orbit by the sun's mass loss, but our planet will be baked sterile, a dead cinder orbiting a bloated dying star. By the time Milkomeda fully forms, Earth will have been lifeless for billions of years. This raises an important question. If humanity or our descendants are going to survive in the long term, we'll need to leave Earth long before these catastrophes occur. We'll need to become a multi-planet species, then a multi-star species, and eventually a multi-galaxy species if we want to hedge our bets against local disasters. The merger of the Milky Way and Andromeda, while unlikely to directly threaten any particular solar system, will reshape our cosmic neighborhood in ways that could make some regions more hazardous and others more favorable for life. The burst of star formation triggered by the merger will create many new stars, some of which will have planets. This could actually increase the number of potential habitable worlds in Milkomeda compared to what the Milky Way and Andromeda had separately. However, the increased stellar density in some regions and the more chaotic orbits of stars could also create hazards. Stars passing closer to each other would disturb the orbits of planets and comets in their solar systems, potentially sending icy bodies plunging into the inner system where they could impact inhabited worlds. The central region of Milkomeda will likely contain a supermassive black hole, even larger than the ones currently at the centers of the Milky Way and Andromeda. When these two black holes, each containing millions of times the mass of our Sun, eventually spiral together and merge, they'll release an enormous burst of gravitational waves, ripples in space-time itself, traveling at the speed of light. This will be one of the most energetic events in the local group's history, though fortunately gravitational waves are extremely weak and unlikely to cause any direct damage to distant solar systems. But here's the big picture. Even after this dramatic merger, even after Milkomeda forms and settles down, we'll still be trapped in the local group. The other dwarf galaxies will still orbit around us. The Triangulum galaxy will either merge with us or orbit nearby, and the vast majority of the universe will still be forever beyond our reach. The collision between the Milky Way and Andromeda is the most significant event in our local cosmic neighborhood's future, but it doesn't change the fundamental isolation imposed by cosmic expansion. In fact, by the time Milkomeda forms, cosmic expansion will have carried distant galaxies even farther away. Clusters that we can barely see today will have faded into darkness. The cosmic horizon will have closed in around us. Future astronomers studying the sky from a planet orbiting a star in Milkomeda will have even less evidence of the broader universe than we do today. They'll live in an era when the universe appears smaller, darker, and lonelier than it does to us. There's something poetic about this. We're living in a special time, a cosmic adolescence, when the universe is still young enough that we can see deep into its structure, old enough that complex life has had time to evolve and contemplate its place in the cosmos, but not so old that the evidence of the universe's grand story has faded beyond detection. Future civilizations billions of years from now won't be as lucky. They'll inherit a universe that has hidden much of its history and structure behind an impenetrable veil of expansion. This makes our current era precious in a way. The discoveries we make now, the observations we record, the understanding we develop about the universe's origin and evolution, all of this might become impossible to replicate in the far future. We're like archaeologists exploring ancient ruins before they crumble to dust, astronomers charting the cosmos before it hides itself away. The knowledge we gain and preserve could become the foundation for understanding that future civilizations can't derive independently from observation. Now let's peer even farther into the future, beyond the merger of the Milky Way and Andromeda, to explore what the ultimate fate of our cosmic prison might be. We're talking about timescales so vast they make the current age of the universe seem like the blink of an eye. We're talking about a future measured not in billions of years but in trillions, quadrillions, even numbers so large they strain our ability to comprehend them. After Milkomeda forms and stabilizes, after the burst of star formation triggered by the collision fades away, the galaxy will enter a long, slow decline. You see, star formation requires raw materials, specifically hydrogen gas that hasn't yet been incorporated into stars. Every time a new star forms, it locks up some of that hydrogen. Some gets recycled when stars die, returned to space through planetary nebulae or supernova explosions, but not all of it. The heaviest stars end their lives as black holes, locking their mass away forever. Even medium-sized stars leave behind white dwarfs, stellar corpses that will never return their material to the cycle of star formation. Over time, the available hydrogen gets depleted. Star formation slows down. The big, bright, short-lived stars become rarer and rarer. In about 100 trillion years, roughly 7,000 times the current age of the universe, the last conventional star will form in Milkomeda. After that, no new stars will be born. The galaxy will slowly dim as existing stars exhaust their fuel and die one by one. The first to go will be the massive blue giants, stars tens or hundreds of times the mass of our Sun. These cosmic beacons burn furiously hot and bright, but they exhaust their fuel in mere millions of years. They've already been dying throughout cosmic history. Then the medium-mass stars like our Sun will fade away, swelling into red giants before collapsing into white dwarfs. This process takes billions of years per star. Eventually, only the smallest stars will remain the red dwarfs. Red dwarfs are the universe's misers. They burn their hydrogen fuel so slowly, so efficiently, that they can shine for trillions of years. A red dwarf with a mass just 1/10 that of our Sun could have a lifespan of 10 trillion years or more. These dim, cool stars will be the last conventional sources of light in Milkomeda, faint embers glowing in an increasingly dark galaxy. But even red dwarfs can't burn forever. Eventually, perhaps 50 to 100 trillion years from now, the last red dwarf will exhaust its hydrogen and fade into darkness, leaving behind a white dwarf corpse. At that point, Milkomeda will contain no living stars, only the stellar remnants, white dwarfs, neutron stars, and black holes, along with failed stars called brown dwarfs that never had enough mass to ignite fusion in the first place. This era is called the Degenerate era by cosmologists. The galaxy won't be completely dark. White dwarfs will still glow with residual heat for a very long time, but they'll be cooling gradually, fading from white to yellow to red to brown to black as they radiate their energy away into space. The galaxy will become a collection of cooling cinders drifting through the void, a graveyard of dead stars. But wait, there's more. Remember that stars in galaxies don't sit still, they orbit the galactic center. Every time two stars pass near each other, they exchange a tiny bit of orbital energy through gravitational interaction. Over extremely long timescales, these interactions add up. Some stars gain energy and move into higher, more eccentric orbits. Others lose energy and sink toward the galactic center. This process, called dynamical relaxation, gradually causes galaxies to evaporate. In about 10 to the power of 19 years, that's 10 billion years, most of the stellar remnants in Milkomeda will have either been ejected from the galaxy entirely or fallen into the central supermassive black hole. The galaxy will dissolve, spreading its corpses across intergalactic space. Those stellar remnants that remain will cluster tightly around the central black hole, a dense core surrounded by mostly empty space. And the universe around Milkomeda? It will be even darker and emptier. Remember, cosmic expansion has been carrying other galaxy clusters away. By this point in cosmic history, tens of trillions of years in the future, every galaxy beyond our local group will have receded so far that their light has completely redshifted into undetectability. An astronomer in this distant era, if such beings could somehow exist, would see absolutely nothing beyond the remnants of the local group. The observable universe would have shrunk to just our immediate cosmic neighborhood, and even that neighborhood would be dark and dying. But the universe isn't done with us yet. There's another process at work, something even more exotic: proton decay. The protons and neutrons that make up atomic nuclei are considered stable particles. We've never observed one spontaneously decay, but many theories in particle physics predict that protons should eventually decay into lighter particles just over timescales far longer than the current age of the universe. The most optimistic estimates suggest protons might have a half-life of 10 to the power of 34 years or longer. If protons do decay, then everything made of normal matter, the white dwarfs, the rocky planets, the very atoms themselves, will eventually disintegrate. A white dwarf, maintained against gravitational collapse by the quantum pressure of electrons, would suddenly find its atomic nuclei falling apart. The star would collapse further or possibly even explode as the decay released energy. Over unimaginably long timescales, all ordinary matter would vanish, converted into radiation and lighter particles that disperse into the void. What would be left? Black holes. These gravitational monsters, formed from the most massive stars and from the cores of galaxies, don't decay through proton decay because they're not made of protons. They're made of pure curved space-time, singularities wrapped in event horizons. In the far future universe, after all the stars have died and even their corpses have decayed away, black holes might be the last organized structures remaining. But even black holes aren't eternal. In 1974, Stephen Hawking discovered that black holes emit radiation through quantum effects near their event horizons. This Hawking radiation causes black holes to slowly lose mass and evaporate over time. The smaller the black hole, the faster it evaporates. A black hole with the mass of our Sun would take 10 to the power of 67 years to completely evaporate. A supermassive black hole like the one at the center of Milkomeda, containing billions of solar masses, would take 10 to the power of 100 years or longer. These numbers are so large they're almost meaningless. To give you perspective, 10 to the power of 100 years is a 1 followed by 100 zeros. The current age of the universe is only about 10 to the power of 10 years, a 1 followed by 10 zeros. We're talking about time scales that are to the current age of the universe as the age of the universe is to the blink of an eye. Actually, that understates it dramatically. These timescales are so long that the entire history of stars, galaxies, and life represents the tiniest fraction of cosmic history, a brief, bright flash at the very beginning of a process that extends almost indefinitely into a dark, empty future. After the black holes evaporate, what's left? According to our current understanding, the universe would contain only the most elementary particles: photons, neutrinos, electrons, positrons, and possibly dark matter particles if they're stable. These particles would be spread across an expanding universe so vast, so diffuse, that the average distance between particles would be larger than the observable universe is today. The universe would approach a state of maximum entropy, maximum disorder, where nothing interesting can happen anymore because there's no energy available to do work. This is called the heat death of the universe. But remember earlier when I mentioned the research from February 2026, suggesting that dark energy might not be constant. If dark energy is changing over time, if it could eventually reverse from pushing space apart to pulling it together, then the universe might not end in heat death after all. Instead, it could end in a big crunch where expansion reverses into contraction, galaxies fall back toward each other, Space itself shrinks and eventually everything collapses back into a singularity similar to the one from which the universe emerged. Henry Tye's calculations suggest this reversal might happen about 11 billion years from now, with the final crunch occurring roughly 20 billion years from today. Now let me be clear, this is highly speculative. Most cosmologists currently favor the heat death scenario. The evidence for a changing dark energy isn't conclusive, but the fact that it's even possible shows how much we still don't understand about the universe's fundamental nature. If the Big Crunch does happen, what would it be like? As space contracts, distant galaxies would stop receding and start approaching. At first, this would be imperceptible, a slight slowing of the expansion. But eventually, galaxies would begin moving toward each other, slowly at first, then faster as the contraction accelerates. Milkomeda would see other galaxy clusters approaching, growing larger in the sky as the universe brings us back together. As the contraction continues, the cosmic microwave background radiation, currently cooled to just a few degrees above absolute zero, would heat up. Space would get warmer. Eventually, it would become hot enough to vaporize planets, then stars. The universe would become increasingly dense and hot, recreating conditions similar to those shortly after the Big Bang, but in reverse. Finally, all matter, all energy, all space-time would collapse into a single point of infinite density, a singularity. What happens after that? Nobody knows. Maybe that's the end, the final period at the end of the universe's story. Maybe a new Big Bang emerges from that singularity, creating a new universe with potentially different laws of physics. Maybe this has happened countless times before, a cyclic universe oscillating between Big Bangs and Big Crunches. These ideas venture beyond what our current physics can address, but they're actively debated by cosmologists trying to understand the deepest questions about existence itself. Let's bring this conversation back to something more personal. What does all of this mean for life, for consciousness, for the possibility that intelligent beings might survive into these unimaginably distant futures? After all, we're not just passive observers of the universe, we're part of it. The atoms in your body were forged in the cores of ancient stars that exploded billions of years ago. You are literally made of stardust, a way for the cosmos to know itself, as Carl Sagan so beautifully put it. So could life in some form persist through the darkening eras ahead? Could consciousness survive the death of the stars, the evaporation of galaxies, even the heat death of the universe itself? These questions push us to the edge of what we can meaningfully discuss, but they're worth exploring because they touch on something fundamental about our place in the cosmic story. In the near term, speaking cosmically, life as we know it depends entirely on stars. Stars provide the energy that drives chemistry on planetary surfaces, the warmth that keeps water liquid, the radiation that powers photosynthesis, and ultimately all complex ecosystems. When the last conventional stars fade and die, any biological life clinging to planets orbiting those stars will face extinction unless it can adapt to radically different energy sources. But here's an interesting possibility. Life might not need stars forever. Consider the white dwarfs that will remain after sun-like stars die. These stellar corpses will stay warm for trillions of years, slowly cooling but still emitting heat. A planet orbiting extremely close to a white dwarf, so close that its year lasts only hours or days, could potentially remain warm enough to support liquid water on its surface. The night sky would be dark, with only the dim glow of the white dwarf illuminating the world, but life might persist. In fact, some scientists have speculated that white dwarf planets might become the most common abodes of life in the far future universe. There will be vastly more white dwarfs than living stars once we get more than a few trillion years into the future. If even a small fraction of them have planets in the habitable zone, that could represent trillions upon trillions of potential homes for life. These worlds would be strange beyond imagination, circling cooling embers in a darkening cosmos, but they might be where the story of biological life reaches its final chapters. What about intelligent life? Could civilizations exist in these far future eras? This is where things get really speculative, but also fascinating. A civilization advanced enough to survive the death of its home star would need to be extraordinarily capable. They'd need to harvest energy from increasingly scarce sources, perhaps collecting every photon emitted by dying white dwarfs, or extracting rotational energy from black holes, or tapping into the quantum vacuum itself, if such a thing is possible. Some physicists have explored the idea of civilizations that gradually slow down their thinking processes to match the decreasing energy availability in the universe. Imagine uploading consciousness into artificial substrates, computers, or structures made from exotic matter that can perform computations using minimal energy. As the universe cools and energy becomes scarcer, these digital minds would run slower and slower, taking millions or billions of years to complete thoughts that once took milliseconds. But here's the fascinating part. From the perspective of those slowed-down minds, time wouldn't feel any different. If your thoughts take 1 billion years but you're unaware of the external passage of time, does it matter? You could theoretically experience an infinite subjective lifetime even as the universe winds down toward heat death. Your thoughts would become infinitely slow, but infinitely many of them could still occur. This is the basis of what physicist Freeman Dyson called eternal life in an ever-expanding universe. However, more recent analysis suggests this might not work. Quantum mechanics imposes limits on how efficiently you can perform computations at low temperatures. There's also the problem of information storage. As the universe expands and cools, maintaining coherent memories requires energy. Eventually, you might reach a point where the energy cost of remembering your past exceeds the energy available, forcing you to choose between forgetting or ceasing to function. Immortality, even for the most advanced civilizations, might have hard physical limits imposed by thermodynamics, but let's think about this differently. What if the goal isn't immortality but legacy? What if advanced civilizations focus not on surviving forever but on leaving something behind, some mark on the universe that persists even after they're gone? This might sound futile after all. We've just discussed how the universe seems destined to end either in cold darkness or fiery collapse. But consider this: information is physical. It's encoded in the arrangement of matter and energy, and some arrangements might persist for unimaginably long times. Imagine creating a message or monument using the most stable possible structures, perhaps arranging black holes in specific patterns that encode information in their distribution and orbits. Those black holes would persist for 10 to the power of 100 years before evaporating. That's long enough to outlast countless cycles of stellar birth and death, long enough to span eras where the universe changes almost beyond recognition. An advanced civilization might encode the story of their existence, their discoveries, their values, in structures designed to outlast nearly everything else. Or consider this even more speculative idea. If the universe does undergo a big crunch, if everything collapses back into a singularity, that singularity might carry information forward into whatever comes next. Some theories suggest that the Big Bang wasn't the beginning of everything, but a transition point from a previous cosmic cycle. If that's true, information from our universe might persist into the next one, encoded in subtle patterns in the initial conditions, like genetic material passed from one generation to the next, but on a cosmic scale. These ideas venture into the realm of what some philosophers call physical eschatology, the study of the ultimate fate of physical systems, including life and consciousness. It's a field that combines physics, cosmology, information theory, and philosophy in ways that can be mind-bending, but at its core, it's asking the same questions humans have always asked. What happens in the end? Is there meaning to existence if everything eventually ends? Can anything truly last forever? Here's my perspective. Even if individual lives, civilizations, even entire universes are temporary, the fact that they existed matters. You matter. The universe brought forth consciousness, gave rise to beings capable of contemplating their own existence and the nature of reality itself. That's extraordinary. The atoms in your body will eventually be recycled, perhaps incorporated into new stars, new planets, maybe even new life forms. Your specific pattern won't persist, but you're part of an unbroken chain of causation stretching back to the Big Bang and forward to whatever ultimate fate awaits us. And here's something that might surprise you. We're living at possibly the most interesting time in cosmic history. Early in the universe, conditions were too hot and chaotic for complex structures to form. Far in the future, conditions will be too cold and dispersed for much interesting to happen. But right now, we're in the stelliferous era, the age of stars, when the universe is filled with light and energy and complexity. Galaxies are forming, stars are being born and dying, planets are coalescing, life is emerging and evolving. This is the universe at its most vibrant, most dynamic, most alive. You exist at a moment when the cosmos is telling its grandest stories, painting its most beautiful pictures across the canvas of space-time. You're part of that story. Every time you look up at the night sky, every time you contemplate your place in the universe, you're participating in the universe's ongoing project of understanding itself. That's not diminished by knowing that stars will eventually die, or that galaxies are trapped by expansion. If anything, it makes it more precious, more meaningful. Think about Earth itself. Our planet has existed for about 4.5 billion years. It will remain habitable for perhaps another billion years before the sun's increasing heat makes it uninhabitable. That sounds like a long time, but it's finite. Does that make the beauty of a sunset less real? Does it make the complexity of life, the emergence of consciousness, the development of art and science and love somehow less significant? Of course not. Temporary doesn't mean meaningless. The same principle applies on cosmic scales. Our local group of galaxies will remain bound together for trillions of years, long after the rest of the universe has receded beyond our reach. Within that local neighborhood, there's room for countless stories to unfold. If humanity, or our descendants, survive and spread to the stars, we could explore thousands of galaxies, settle trillions of solar systems, encounter whatever other forms of life exist in our cosmic bubble. The fact that we can't escape to more distant galaxy clusters doesn't diminish the vastness of what remains accessible to us. And who knows what discoveries await us? Every time we've pushed the boundaries of our knowledge, we've found that reality is stranger and more wonderful than we imagined. A few hundred years ago, we thought the Milky Way was the entire universe. Then we discovered countless other galaxies. We thought the universe was static, then learned it's expanding. We thought that expansion was slowing down, then discovered it's accelerating. Each revelation opened new questions, new mysteries to explore. Maybe someday we'll discover that the laws of physics allow forms of travel or communication we currently think impossible. Maybe we'll find loopholes in the constraints imposed by cosmic expansion, or ways to manipulate space-time that seem like magic today. Or maybe we'll learn to be content with our cosmic neighborhood, finding infinite depth and complexity within the bounds of what's reachable. Both possibilities represent fascinating futures. So what can we actually do right now, today, to better understand our cosmic prison and perhaps find ways to push against its boundaries? What missions, telescopes, and experiments are scientists conducting to probe the nature of dark energy, cosmic expansion, and the ultimate limits of what we can reach? This is where cosmic philosophy meets practical science, where speculation gives way to observation and measurement. Let's start with the most powerful tools we have for studying the universe: telescopes. The James Webb Space Telescope, launched on Christmas Day in 2021, has revolutionized our view of the cosmos. Positioned at a gravitationally stable point about 1.5 million kilometers from Earth, Webb uses its enormous 6.5-meter mirror and ultra-sensitive infrared detectors to peer deeper into space and farther back in time than any previous observatory. Webb is particularly good at detecting the most distant galaxies, those whose light has been traveling toward us for over 13 billion years, showing us what the universe looked like when it was less than a billion years old. These early galaxies appear as faint smudges in Webb's images, but they contain crucial information about how the first structures formed, how dark matter shaped the evolution of galaxies, and how the expansion of space has affected light traveling across cosmic distances. In February 2026, Webb has been operational for over 4 years, and its discoveries have consistently surprised astronomers. It's found galaxies that formed earlier and grew larger faster than theoretical models predicted, suggesting we don't fully understand the processes that governed the early universe. It's detected complex organic molecules in the atmospheres of distant exoplanets, planets orbiting other stars, bringing us closer to answering whether life exists elsewhere. And it's provided unprecedented measurements of how fast the universe is expanding, data that's central to understanding dark energy. But Webb isn't alone. Ground-based observatories continue to make vital contributions. The Vera C. Rubin Observatory in Chile, which began operations in 2025, conducts the Legacy Survey of Space and Time, a 10-year project to photograph the entire visible southern sky every few nights. This creates a constantly updating map of the universe, allowing astronomers to spot anything that changes. Supernovae exploding, asteroids moving through our solar system, even distant galaxies brightening or dimming as their central black holes devour matter. The Rubin Observatory is particularly important for understanding dark energy. By detecting millions of distant supernovae and measuring their properties, it provides data on exactly how the expansion rate has changed over cosmic history. This helps determine whether dark energy is truly constant or whether it's evolving over time, which, as we discussed earlier, has profound implications for the universe's ultimate fate. Then there's the European Space Agency's Euclid mission, launched in July 2023. Euclid is specifically designed to map the dark universe, studying both dark matter and dark energy by observing billions of galaxies across more than 1/3 of the sky. It measures how gravity from dark matter bends the path of light from distant galaxies, creating subtle distortions that reveal where dark matter is concentrated. And by tracking how the large-scale structure of the universe has evolved over time, it constrains the properties of dark energy. NASA's Nancy Grace Roman Space Telescope, scheduled to launch in 2027, will join this effort. Roman will have a field of view 100 times larger than Hubble's, allowing it to survey vast regions of sky quickly. Its primary mission includes mapping the distribution of galaxies to understand dark energy, searching for exoplanets using gravitational lensing, and observing the universe in infrared light to study everything from nearby planets to the most distant galaxies. These missions all contribute pieces to the puzzle of cosmic expansion. But perhaps the most fundamental question they're addressing is this: what exactly is dark energy? Is it truly Einstein's cosmological constant, a property of empty space itself that never changes? Or is it something more dynamic, a field that varies over time and space, something physicists call quintessence? The difference matters enormously for understanding both our cosmic prison and the universe's ultimate fate. If dark energy is the cosmological constant, it will continue pushing the universe to expand faster and faster forever, making the heat-death scenario almost inevitable. But if it's quintessence, if it can change over time, then other possibilities open up. Maybe dark energy will weaken in the future, allowing expansion to slow down even if it never reverses. Maybe it will strengthen, leading to a Big Rip scenario where expansion accelerates so much that it eventually tears apart galaxies, stars, planets, even atoms. Or maybe, as some recent research suggests, it could reverse entirely, leading to the big crunch we discussed earlier. Current observations slightly favor the cosmological constant interpretation, but the error bars are still large enough that we can't rule out alternatives. Every new measurement from Webb, Euclid, Roman, and other observatories helps narrow down the possibilities. This is science in action, using the most advanced technology humanity can muster to answer questions about the nature of reality itself. But observations alone aren't enough. We also need theoretical physicists working to understand what dark energy actually is at a fundamental level. This connects to some of the deepest problems in physics, particularly the challenge of reconciling quantum mechanics, which describes the smallest scales of reality, with general relativity, which describes gravity, and the largest scales. Many physicists believe that dark energy is somehow related to the quantum properties of empty space, to the vacuum itself. Quantum field theory predicts that even empty space should be filled with virtual particles constantly popping into and out of existence, creating what's called vacuum energy. You can actually measure this energy indirectly through effects like the Casimir force, where two metal plates placed very close together in a vacuum experience an attractive force because the space between them excludes certain wavelengths of virtual particles. The problem is that when physicists calculate how much vacuum energy there should be, they get an answer that's about 10 to the power of 120 times larger than the dark energy we actually observe. This is arguably the worst prediction in the history of science, off by 120 orders of magnitude. Something is clearly wrong either with how we're calculating vacuum energy, or with our understanding of what dark energy actually is, or with how quantum mechanics and gravity interact. Solving this problem might require a theory of quantum gravity, a framework that successfully describes how quantum mechanics operates in the presence of strong gravitational fields and curved space-time. Several approaches to quantum gravity are being developed. String theory proposes that fundamental particles aren't point-like but are actually tiny, vibrating strings, and that the universe has additional spatial dimensions beyond the three we perceive. Loop quantum gravity tries to quantize space-time itself, suggesting that space and time are made of discrete units at the smallest scales rather than being continuous. Other approaches, like causal set theory or emergent gravity, propose even more radical reimaginings of what space and time fundamentally are. None of these theories are complete yet, and we don't have experimental evidence that definitively favors one over the others. But if we can develop a working theory of quantum gravity, it might help us understand dark energy, and that understanding could potentially reveal whether the constraints trapping us in our local group are as absolute as they currently appear. Maybe, just maybe, a deeper understanding of physics will reveal loopholes we haven't imagined yet. This is why funding basic research in theoretical physics matters, even when the practical applications aren't obvious. The scientists working on these problems aren't trying to build faster spaceships or more efficient solar panels, at least not directly. They're trying to understand how reality works at its most fundamental level. But history shows that this kind of deep theoretical work eventually leads to technological revolutions that change civilization. Einstein's theory of relativity seemed like pure abstract mathematics when he published it in 1905 and 1915. But today, your smartphone's GPS wouldn't work without accounting for relativistic effects on satellite clocks. Quantum mechanics appeared to be bizarre philosophy when it was developed in the early 20th century. Now it's the foundation of all modern electronics, computers, and countless other technologies. Whatever we learn about dark energy, quantum gravity, and the structure of space-time might seem impractical today, but could be transformative tomorrow. Meanwhile, experimental physicists are conducting tests on Earth to probe fundamental physics. The Large Hadron Collider near Geneva, Switzerland, smashes protons together at energies approaching what existed fractions of a second after the Big Bang. These collisions create exotic particles that only existed in the early universe, allowing physicists to test theories about how the fundamental forces operated under extreme conditions. Future colliders, if built, would reach even higher energies, potentially discovering new particles or forces that could reshape our understanding of the cosmos. Gravitational wave observatories like LIGO in the United States, Virgo in Italy, and Kagra in Japan detect ripples in space-time created by colliding black holes and neutron stars. These events release more energy in gravitational waves in a few seconds than all the stars in the observable universe emit in light. By studying these waves, scientists learn about the properties of the most extreme objects in the universe and test general relativity under conditions where gravity is strongest. The planned space-based gravitational wave observatory LISA, scheduled to launch in the 2030s, will detect much longer wavelength gravitational waves from supermassive black holes merging and potentially from the early universe itself. These observations might reveal whether the Big Bang was truly the beginning or whether it was preceded by something else, a previous universe, a period of inflation, or something we haven't yet imagined. All of this research, from the most powerful space telescopes to the most sensitive gravitational wave detectors to the deepest theoretical work in physics, contributes to answering the question we started with: why are we stuck in the Milky Way forever? The answer, as we've seen, involves the expansion of space, dark energy, the finite speed of light, and the fundamental structure of the universe itself. But science is an ongoing process. What we understand today forms the foundation for what we'll discover tomorrow. But I want to leave you with a different perspective, one that's more hopeful and empowering than you might expect, given everything we've discussed. Yes, we're cosmically isolated. Yes, the universe is expanding in ways that lock us out of most of its wonders. Yes, the ultimate fate of everything seems to be either cold darkness or fiery destruction. But none of that diminishes the extraordinary nature of existence itself or the profound opportunities that remain available to us. Let me put this in perspective. Our local group contains approximately 2 to 3 trillion stars spread across more than 50 galaxies. If even 1 in a million of those stars has a habitable planet, that's still millions of potential homes for life. If intelligent civilizations are even moderately rare, say 1 per galaxy on average, that's still 50 potential alien cultures within our cosmic neighborhood, waiting to be discovered if we can develop the technology to reach them or detect their signals. The Milky Way alone, our home galaxy, contains somewhere between 100 billion and 400 billion stars. At our current rate of exploring them, we've studied perhaps a few thousand in detail, less than 1/1,000,000% of what's available. We're like someone standing on the shore of an ocean, having examined a single grain of sand, declaring they understand everything about the sea. We've barely begun to explore even our immediate cosmic neighborhood. And Earth itself, this small world orbiting an average star in an unremarkable part of the galaxy, contains mysteries we're only beginning to unravel. We've identified perhaps 10% of the species living here, maybe less. We don't fully understand how consciousness emerges from neural networks. We haven't solved the origin of life or determined whether it exists elsewhere in our solar system, perhaps in the subsurface oceans of Europa or Enceladus. We don't know how to prevent our own extinction or how to build sustainable civilizations that could last for millennia. In other words, we have work to do right here, problems to solve, discoveries to make, before we need to worry too much about being trapped in the local group. The fact that we can't reach the Virgo cluster doesn't mean we've run out of frontiers. It just means our frontier is defined differently than we might have imagined. Think about the progression of human exploration. For most of our history, individual humans rarely traveled more than a few dozen kilometers from where they were born. The next valley, the neighboring tribe, these were distant mysteries. Then we learned to sail oceans, discovering that Earth is far larger and more diverse than any single culture imagined. Then we developed aviation, making the entire planet accessible within hours rather than months. Then we reached space, landing on the moon and sending probes to every planet in our solar system. Each of these expansions of our frontier changed how we thought about ourselves and our place in the world. Each revealed new possibilities, new challenges, new questions to answer. The fact that Earth is finite, that you can't sail forever in one direction without eventually circling back to where you started, doesn't make terrestrial exploration meaningless. Similarly, the fact that our cosmic frontier is bounded by the local group doesn't make space exploration futile. In fact, I'd argue it makes it more important. If we're stuck in this cosmic neighborhood, we'd better take good care of it. We'd better not destroy ourselves before we have a chance to explore it fully. We'd better preserve the knowledge we're gaining about the universe while we still can, because, as we discussed, future civilizations billions of years from now won't be able to see what we can see today. The cosmic microwave background, the distant galaxies, the evidence of the Big Bang, all of it will fade beyond detection given enough time. We're living in a precious window, a brief cosmic moment when the universe is both old enough to have developed complexity and young enough to still reveal its history and structure. That makes us, everyone alive today, extraordinarily lucky. You have access to more information about the universe than any human who lived before the 20th century. You can see images of galaxies billions of light years away, captured by telescopes that didn't exist a few years ago. You can learn about the fundamental forces governing reality, insights that required centuries of brilliant people building on each other's work to achieve. And this knowledge isn't just accumulating in university laboratories and observatories. It's available to anyone with an internet connection. You can access research papers, telescope data, educational resources that would have required traveling to specialized libraries or institutions just a generation ago. You're living at a moment when humanity's collective understanding of the cosmos is advancing faster than ever before, and that understanding is more democratically accessible than at any previous point in history. So what should we do with this knowledge? How should we respond to the realization that we're trapped in a finite cosmic prison? I think there are several answers, all of them important. First, we should continue exploring. Even if we can't escape the local group, we've barely begun to explore our own solar system, let alone the hundreds of billions of stars in the Milky Way. Every mission to Mars, every probe sent to the outer planets, every new exoplanet discovered expands our understanding and reveals new possibilities. We should invest in these efforts, support the science and engineering that makes them possible, and inspire the next generation to continue the work. Second, we should take care of Earth. This planet is the only home humanity has ever known, and it might be the only habitable world we'll ever personally experience. The fact that other potentially habitable planets exist light years away doesn't help us if we destroy this one through climate change, nuclear war, or ecological collapse. Our cosmic perspective should make us appreciate Earth more, not less, should motivate us to be better stewards of the only world we can currently reach. Third, we should preserve and transmit knowledge. The universe is hiding its own history as cosmic expansion carries distant galaxies beyond our view. We need to record what we learn, teach it to future generations, ensure that the hard-won insights of our era aren't lost. This means supporting education, libraries, archives, museums, all the institutions that maintain humanity's collective memory. It means making science accessible and exciting, helping people understand their cosmic context. Fourth, we should stay curious. Every answer we find opens new questions. Every mystery we solve reveals deeper mysteries. The fact that we now understand why we're trapped in the local group is itself a recent discovery, the product of observations and theories developed mainly in the last few decades. What will we understand in another few decades? What discoveries will future generations make that we can't even imagine today? And finally, we should find meaning not in immortality or infinity, but in the temporary and finite nature of existence. You don't need to last forever to matter. The atoms in your body have been part of stars, planets, oceans, countless other life forms before becoming you. After you die, those atoms will continue their journey, participating in new structures, new stories, You're a temporary pattern, but you're part of an unbroken chain of causation stretching back to the Big Bang and forward to whatever ultimate fate awaits the universe. That's not depressing, that's profound. You're the universe experiencing itself, consciousness emerging from matter, asking questions about its own existence and nature. The fact that this doesn't last forever doesn't make it less real or less meaningful. If anything, the temporary nature of consciousness makes it more precious, more worthy of appreciation and celebration. So, yes, we're stuck in the Milky Way and the local group. Yes, most of the universe is forever beyond our reach. Yes, everything eventually ends. But between now and that eventual ending, there's an almost unimaginable amount of space to explore, knowledge to gain, experiences to have, and meaning to create. The cosmic prison we find ourselves in is still incomprehensibly vast, filled with wonders we're only beginning to discover. The universe gave rise to stars, planets, and life. It created you, a conscious being capable of contemplating your place in the grand cosmic story. That's extraordinary. Don't let the vastness of what you can't reach overshadow the magnificence of what you can experience, learn, and contribute during your brief time as a conscious pattern in the cosmos. We've covered a lot of ground in this conversation, from the mechanics of cosmic expansion to the distant future of the universe itself. But our journey doesn't have to end here. If you want to dive even deeper into these questions, especially the practical challenges of actually traveling between stars within our cosmic neighborhood, make sure to watch my video called The Big Problem with Interstellar Travel Nobody Talks About. The video is at the left side of the screen. In that video, I explore the engineering, physics, and existential challenges that stand between humanity and the stars, the obstacles that remain formidable even within our gravitationally bound local group. It's a perfect complement to what we've discussed here. See you there.